Swayam Prabha. Digital India. Educated India.
Good morning. So, today we will be discussing a additional point in fluid flow through vacuum systems. What is this additional point? We have already discussed the concept of conductance. We have discussed laminar flow, which is called continuum flow. We also said at that time turbulent flow can occur in the initial few seconds, we may not worry about it because time is not much. Then we said in molecular flow, which is very important for high vacuum applications, the conductance is independent of pressure, whereas in viscous flow conductance was dependent on pressure. So, all these concepts through suitable equations in terms of Poiseuille's law and kinetic theory and molecular flow conditions, we have taken statistical criteria. So, we have given you lot of formulae. So, you should use these formulae to get the conductances of the interconnecting piping network between pump and the chamber. Once you get that, you can calculate effective pumping speeds, and once you get effective pumping speed, you can get the pump down characteristics, which is the main aim of this exercise. So, this fluid flow in vacuum system, this entire module, why we have created for you just after the production of the pumps, because at this stage you should know how well actually these pumps are not connected directly to the chamber, they are connected with a piping network. So, finally, neither the pump matters nor the chamber matters, they should be of good quality, no doubt about it, but it is the interconnecting pipe that matters a lot. Okay. It is between two railway stations, both the stations are very good, train is also very good, but if track is not good. So, the connecting pipe, if it is bad, as I told you in the last lecture also, crores of rupees that you spend in very good quality pumps, particularly in high vacuum pumps, and crores of rupees you will be spending in very high quality chambers with metallic gaskets and all that effort is in vain, because you have used a wrongly calculated interconnecting pipe of a small cross section and quite a big length, just because you want to be comfortable, you do not want to hear the sound or something, you have put the pump somewhere. No, vacuum technology will not spare you if you do such mistakes, it will just not give you vacuum. The only problem in vacuum technology is you do not get vacuum, then you cannot start semiconducting process, you cannot start nuclear processes, you cannot do any space simulation, you cannot do any metallurgical melting, casting, etc. You cannot do vacuum distillation, you cannot do drying. So, all the industries get stuck, no electronics, no space technology, no nuclear technology, because unless you do the experiments in the R&D laboratories under high vacuum conditions, which are there in the actual conditions of application, you cannot simply start any activity. So, over a period of time, lot of importance was given to these conductance calculations under the broad name of fluid flow in vacuum systems. This is purely a fluid mechanics aspects of it, but of course, I remind you, I have already told you last time also, it is not a continuum fluid anymore once you come to 0.1 torr. But a typical mechanical engineer will tell 99.999% of the gas is being removed, sir. Why I should bother about this 0.01% of this gas and enter into molecular flow, this flow, that flow, why are you making my life difficult? But the problem is all the high tech is there in that 0.01. Only mechanical operations, little bit of thermal operations like this thermos flask, etc. So, thermal mechanical applications are there, lifting, etc. But real applications of electronics, space, nuclear, all of them are in that metallurgy, they are all in the 0.1 torque, including molecular distillation, which is coming up in a big way in a pharmaceutical sector. They are all in below 10 power minus 2 torque. So, while doing that, if you make a mistake in the conductance of the pipe, you will take, instead of 10 minutes, it will take 2 hours to get the evacuation. And at times in big space simulation chambers, if you make a mistake in the interconnecting pipe, you will end up in getting 3 days, 4 days to get an acceptable vacuum before you do some simulation experiments of a satellite in a big chamber. So, you must be very good in proper designing of interconnecting pipe and through rigorous calculations and trying them in a small scale and then go into a very big scale. Otherwise, very big particle accelerators of 1 kilometer diameter type of thing of a nuclear particle accelerators like LSC experiment, etc., huge chambers and 10 power minus 8 torr. If it takes 2 months, 3 months to evacuate, then you cannot do any meaningful experiment. Anyway, I am giving all this because I want you to understand the importance of fluid flow in vacuum systems and the concept of conductances and its calculations. In fact, this is the only place in vacuum technology where we will be discussing some maths in addition to physics and chemistry. Later, either we will do physics or chemistry or some materials handling, etc. Okay. So, as we already discussed the concept of conductance and laminar flow and molecular flow, there I mentioned, if you remember, otherwise you can see the lecture number 31 and 32. I mentioned while transition from laminar flow to molecular flow, in between there is a transition flow, where it has got some characteristics of laminar flow as well as molecular flow. It is like Reynolds number more than 2200, less than it, there is nothing like clear distinction. In between there is a transition, even between turbulent and laminar flows, there is no clear boundary, there is a transition. It depends on the situation, gas, and if there is a fanning or any such things, even in fluid mechanics, there will be changes. So, there is a broad range only. Same thing here in vacuum technology. First turbulent flow, which we are not bothered because there may be few minutes, instead of few minutes it may take 10 minutes, how does it matter? We are going to evacuate for 20 hours. But just at that transition, even in the initial turbulent to this one, at times we may get choked flow, that is somewhat turbulent, but it occurs when the passage is choked. Even in turbulent conditions, when passage is choked, those people who are dealing with in aeronautical engineering and mechanical engineering, they know what is choked flow. If the cross section for the flow is suddenly choked and the pressure ratios are, if it is very high, that means the pressure drop is not a small pressure drop that we normally calculate in CFD, like delta P is maybe 1% of P, that is different, but delta P is huge compared to even the P average. Then we enter into a situation where compressibility comes into picture. So, that time we get some strange situations that flow rate is independent of pressure drop. That means, one side you have got atmospheric pressure, other side whether it is 10 power minus 1 or minus 2 or minus 3. If it is a choked condition, you will get a constant flow rate. Okay. Why this happens and what all that goes into that, there is a lot of theory behind it. I am not going to deal with this compressibilities and CFDs and how all these flows are interrelated. It can be done, it will take some 10 to 20 hours. But today I am going to give a brief introduction of transition flow and the choked flow, which normally are ignored in day to day life, but it plays a very important role when you are dealing with very clean systems, very large systems, very large vacuum pumps, and if you want to avoid some particulate not to enter into pumps, or you want to take precautions that your pumps, your systems will work for years together without any problem, because you are a good engineer. At that time you have to understand that. That means, there is a gradual change from turbulent, choked, laminar, transition and molecular. Sometimes in some applications molecular flow is the main thing, some applications it is only transition flow, some applications it is laminar flow. Okay. In very high pressure, but under vacuum like 600 torr, 700 torr, it is not a big vacuum, but still it is subatmosphere, like when you are using cleaners, vacuum cleaners and all. Intentionally they create such poor vacuum, so that there is a lifting action, etc. So, some whirling, swirling action will be there to pick up the dust, etc., because the force concepts come there and all. There we enter into variety of flows. So, all these things must be understood to an engineer, those who are dealing with process applications in using vacuum. Okay. So, in today's talk, the concepts that are being covered are transition flow, for which we normally associate the famous scientist Knudsen, because it is also called Knudsen flow, who has given a Knudsen number to us like Reynolds, like lambda by d. Lambda is the main free path in vacuum technology and d is the characteristic diameter of a, if it is a diameter of a circular pipe, otherwise it is a hydraulic diameter. Then transition flow conductance through a pipe, just like we have calculated in 32 lecture viscous flow conductance, 33 lecture molecular flow conductance. Here we will find out transition flow conductance, because it has to be done, it has to come from laminar, enter into molecular through transition only. And also choked flow conditions at times we face, not always, that time we have to understand concepts of fluid flow. Okay. There we do not directly talk of conductance like conductance, but indirectly these are all involved. It is basically resistance to flow. Okay. In a way that is also conductance, but we normally deal with compressibilities and other things come into picture in those equations. But I am telling, I am not going to cover all these things in this half an hour period, but these are the points to be covered, and you can get in internet all varieties of explanations for all these flows. Finally, we will be doing some conclusions based on these points relevant to vacuum technology when it is applied to process applications. Okay. This figure we have seen already earlier also in beginning when we are dealing with the fluid flow, where we have seen the figure very clearly. You can again see this. This is a continuum flow, laminar flow, and this is a molecular flow, and this is a Knudsen flow. These two flows we have discussed in lecture number 32 and 33. So, I am not going to describe it again, and if you want to understand more, you please go through those lectures again. Briefly speaking, here there is a continuity and here there is a sort of discontinuity, because each molecule is independent. Some molecules can come back also, it depends on the local roughness there. There is nothing like flowing across pressure drop, etc. Pressure drop is not the main reason for flow. It is only the molecular concentration differences and statistical chances for left to right and right to left movement of molecules here, that is called molecular flow. It is purely statistical, whereas here pressure drop is responsible, and in between there is sort of flow where we get the concept of pressure drop being responsible for the flow. We also get the concept of free statistical chances of molecules going from relatively a poor vacuum to a high vacuum side. There is also pressure drop finally, but the pressure drop is not the driving force. So, there is some signature of molecular flow situation, there is some signature of laminar continuum flow. So, that is called Knudsen flow or intermediate flow or transition flow. Okay. And that normally comes in the Knudsen number 0.01 less than Knudsen number less than 0.5. Continuum flow and molecular flow we have already discussed earlier. So, this transition flow sometimes is very important. If your vacuum is in the order of 0.1 torr, that is the main vacuum, and suddenly initially it got evacuated fast and it got stuck. Such situations, this transition flow plays an important role. So, you may have to use these equations in such situations, but for high tech applications you will cross all these flows very fast by using boosters and again releasing the booster and use only high vacuum pumps. There is a way of doing it that we will see when we discuss the applications in detail. When to introduce a booster, when to take out the booster unnecessarily, when to reduce the electrical power, all these things in an overall system design we will calculate for different applications. But keep in mind that molecular flow style is different and laminar flow style is different. And again I am telling you 99.99% is already removed by the time we crossed the laminar flow, but no application has started. That is the beauty of vacuum technology. Okay. Okay. In transition flow, just like calculations of conductance in other flow regions, there are some equations for here. Here I intentionally changed little bit of units here. Here diameter I am taking in inches, because I want students to also do various types of calculations. I cannot tell d is in centimeter always throughout 60 lectures. I cannot tell always use only tar or only millibar. Sometimes I will intentionally use some micron or atmosphere or PSI. Okay. You have to be expert in conversion of these units. That is engineering, because when you go to a customer, particularly a company engineer, they will not listen to you. They will say 1 inch pipe, 2 inch pipe. At that time you cannot say that wait for some time. You should have an idea of doing all that. That is why I am giving here for air. Why I have taken air? Most of the vacuum technology they will remove air only. So, these conditions I have given, I have taken from lecture number 32 and lecture number 33, but original equations are there hidden. If you want, you can go there and use for different gases. I have used it for air. So, all that R, T and room temperature. So, everything has been taken into account to get a constant number called 3000, because I am using a finite gas at finite temperature. So, once these two are fixed, then you can fix other terms. Only the dimensional terms will be there and pressure will be there in the laminar flow, pressure term will not be there in the molecular flow. But when if you are a chemical engineer, if you are operating a chemical vapor, this should not be used as it is, but concepts are clear. You have to go to 32, 33. If you have got any confusion, you can always contact me. Anyway, there will be quizzes and other things when you take up this course, because in vacuum technology is so wide and broad and lot of things. I cannot tell everything like very clear way. There will be lot of dependencies. After some time you will see degassing, that is also a flow. Something is coming from the gas surfaces, it is not a volumetric flow, something is leaking from the outside. So many varieties of problems are there, you have to parallelly consider, but everything is following certain mathematics, physics, chemistry. Whether you will go up to what depth, it is up to you. If you are a very high tech person, you have to do that. Okay. So, for example, for air, when the dimensions are taken in inches, the viscous flow conductance, that is called laminar flow conductance, we dealt already in 32 lecture, is 3000 times P average. That means, if there is a delta P across a pipe, P average is the average pressure, P 1 plus P 2 by 2. We have seen in Poiseuille's law also there. So, that is 3000 times P d to the power of 4 by L in liters per second. You can convert into meter cube per hour also, depends on the unit that particular company likes. See, different companies like different units for historical reasons or sentimental reasons. You cannot find fault with them, because they will not like simply other units. Okay. They will have trust on certain unit. Okay. Okay. So, for molecular flow, it is 80 d cube by L, but one thing is constant, molecular conductance is third power of diameter and inversely proportional to length. Viscous flow is fourth power of diameter, proportional. Proportionality constants change with respect to operating temperatures, with respect to nature of gas, molecular weight of the gas. If it is mixes, some additional complications are there. We will see all these things as we proceed to the applications later, but here I am taking for air. So, in transition flow, as I told you, you have to take average of the, not average, you have to take, because both the things are available parallelly, both of them are operating. So, you will have to add them. It is as simple as this, but whether it works or not in your situation, if it is not working, you cannot find fault with mass. You have made some additional things, that is why it may not be working. You might have got a choked conditions, which we will see later. Without your knowledge, you have to solve it. So, simply saying, sir, I have used these things, my pressure versus time curve is not matching. Maybe there is a leak in the chamber, maybe your pump is not working for some time, you have taken some effective pumping speed, maybe your pipe is very rough, okay. maybe your gauge is not working. So, vacuum not coming has got several reasons. An intelligent engineer, an expert in vacuum technology, after going through this course should be able to quickly go to that. That we will show you in troubleshooting of vacuum systems. But these are all interrelated: fluid flow, production of vacuum, measurements, system design, components, they are all interrelated. You must be able to do that. So, this is what very clear this figure shows. In viscous flow, conductance is a function of pressure, that is why it varies with linearly, and molecular flow is independent of that, and respective units are given, and transition flow comes in between, non-linear zone. This happens in several situations in physics, when two terms are competing, in between there will be a third phase. Okay. So, we have understood this transition flow. There is one more interesting flow which normally nobody bothers, but sometimes we need to worry in space technology or even nuclear, or when you are using huge capacity pumps, or when there is a worry that some particles may enter into your pump, because you are suddenly switched on, some dust has entered, sir, you have told so many things and I have switched on something and pipe I have not cleaned maybe, and I am getting now pump is stopped, chamber is not good, vacuum is not coming, nothing is happening, no process, no customer, my boss has asked me to go out of my place. Such situations will come, particularly that is choked conditions. Okay. So, there is a choked flow. Vacuum technology is very complicated. Choked flow may come or may not come, but you may have to do intentionally choked flow at sometimes. We will see what it is now. Relevant to vacuum technology. There is a choked flow in other region also, even in high pressure physics and aeronautical engineers, they know very well the choked flow situations. Okay. During the landing and during the takeoffs and during the and rockets, etc. There are a lot of places choked flows will come there. What is choked flow? Basically, when there is two zones of two pressures with the necessary density of the gas, whatever fluid that you are taking at temperature T naught. When there is a restricted, though I have shown here schematically, I call it as a restricted thing. It is not like a pipe, it is not like a conducting pipe, it is not like a conducting network, a sort of piping network. It is a restriction is there. That means, some constricted flow is there, choked flow is there. So, if the orifice cross sectional area here separating two areas, or if there is a small element with a restricted area, in these two conditions, when pump is connected here and the other side source of gas is coming here, we end up in choked flow situations. Why we end up here? The pressure drops are huge, unlike normal pressure drops in laminar flow in 32 lecture and 33 lecture, etc. The delta P is maybe 1% of the average P. Here it is not like that, it may be 50%. So, the delta P when it is huge, you will enter into a limit of situations where compressibilities start coming into picture. So, compressibilities cannot be neglected with flows through apertures or short ducts that separate regions between two chambers working at two pressures, but the pressure values are quite different. That means, huge pressure difference may be there. When such situation will come in vacuum, our highest pressure is atmosphere. So, it can be only low, but atmosphere one side 10 power minus 1 torr one side, huge pressure drop for us. For a high pressure engineers it is only 1 atmosphere drop, but for us that is the maximum pressure difference. If that is occurring in a small constriction of an area of an orifice or a small element, we enter into this choked flow, not be a beautiful pipe, where there we will not enter into choked flow. Such situations choked flow is often encountered, and in various applications of vacuum technology we get into these situations, sometimes intentionally. For example, when you are venting it, a chamber, suddenly you are rushing the air atmosphere inside, that is this situation here. And if you restrict that venting through a small port, this may be the situation. If there is a leak and fairly big, but not big at all, it is a micro leak or something, 0.1 millimeter or something, and thickness of the chamber may be this, that this is equivalent to a sharp pipe of a small cross section. That time one side atmosphere, other side vacuum. It may be 10 power minus 1 torr for rough vacuum people, it may be minus 6 torr for high vacuum people. That time this situation will come. So, at that time it is a choked flow. And what is so great about it? In one point we can tell, after a level of vacuum, the throughput is constant, whether you get minus 1 or minus 2 or minus 3, one side atmosphere, throughput will be same. When it will be same, after crossing what pressure it will same, we will see the physics in the next slide. And these situations are normally encountered in venting situation or gas inlet. You are intentionally entering into a gas inlet without disturbing the vacuum. I want to introduce gas. How do you do that? You have to have a valve, but that valve is not a shut off valve or anything. That is gas inlet valve. It is like a needle valve, okay, very restricted flow. You may enter into choked flow there. And sometimes debris not to go into the pump, we may have to initially choke it and slowly open that, so that after some time it is freely evacuating. When you are introducing huge vacuum pumps to connect it to a relatively smaller volumes, etc., you may enter into such situation of some particles may go there, even some material which is a costly material inside your process may go there. So, such situations to be avoided, you have to intentionally create choked flow. But choked flow characteristic is the throughput is independent of pressure drop once you cross a critical pressure. That is the most important point. That means, it can be used beautifully, a constant throughput device, constant pumping speed device in an equivalent way, like that. That pumping speed means conductance, conductance unit is same as pumping speed. So, the pumping speed as seen from the source can be a constant, just because it is independent of vacuum level. Independent of vacuum level minus 1 or minus 2, pumping speed can be made constant. We will see those situations in the applications. So, as I have already explained you, when the discharge pressure is 0.5 times the upper side pressure, we enter into choked flow. This has been explained already. So, you please go through this English. This happens when the flow velocity in the restriction is equal to sound velocity, because that is where Mach number 1 is crossed. These are all interrelated, basically compressibility, sound velocity and restrictions and choked flow, these are all related, and turbulence in a way. So, fluid mechanics people know how to deal with that using various CFDs, etc. But in vacuum technology, we have to be very careful in applying standard technologies. Okay. Under high vacuum, no viscosity, but atmosphere viscosity. So, we have to be careful, MFD, CFD, everything together we have to use, and formula to be used judiciously, and reiterative calculations before you select the pumps and chambers. That is where the vacuum technology engineer is much more scientific and technologically competent and with engineering skills. Then only you can go for high tech industries. So, once you cross this PD less than 0.53 pu, even if PD discharge side pressure is reduced, throughput remains constant and it will result in constant pumping capacity. That is what is plotted here, and sometimes it is customary to put 1 here and 0 this side, but it is okay. That means, initially both side atmosphere, no flow, pressure drop is not there. So, pressure will be 0, and this is the maximum possible thing with condition of choked condition C, and that maximum is considered as O Q naught. So, Q by Q naught in a normalized conditions, I have plotted this curve, because different Q naughts may be there, and Q by Q naught will be always a particular factor. So, this will be applicable for various situations, various pumps, various chamber volumes, various constrictions, but it should be a constriction. Then once P by P naught crosses 0.5, you will enter into choked flow. So, choked flow means what? Between 1 and 0.5, you are getting variable throughput, but once you cross 0.5, that means high vacuum. This is high vacuum side, this is poor vacuum. Do not get confused, this is not P, this is P by P naught plotted, this side is the atmosphere. Okay. for your convenience. You can also show like this, but I have shown like this because it gets saturated. I want to show that as vacuum is improved, the flow rate gets saturated. Increasing the vacuum will not result in additional thing. If you want to increase this value, you have to increase the PU, because the formula for the choked flow conditions PU comes into picture. Okay. So, all those things if you follow properly, you can have a controlled flow rate. When large pumps are needed for applications in which initial pumping from atmosphere pressure might create turbulence, huge turbulence, so that some airborne debris may enter into that. If you want to avoid, choking can be used as a facility to limit the throughput, so that slowly small amount of debris may enter, the pump can handle it. But if you introduce huge debris, the pump gets stuck. There are some pumps which can handle particulates like screw vacuum pumps. Some particular amount of particulate it can handle, because there are gaps. These are dry pumps, there is no lubrication, there is a gap between that. Roots blowers, they can handle, but if you increase the particulate huge amount, they will fail. Watering pump can handle the debris, but rotary pump cannot handle, because it is physically touching and it will scratch, and the pumping action will be ceasing and oil get spoiled. Okay. Then you have to again open the whole thing. So, you can avoid by slow and steady start. Okay. This is the thing. I just want you to be careful before you start operating pumps and designing the pipes. So, these two aspects called transition flow and choked flow we have considered for your benefit, so that you are aware of these things. Sometimes it may not be needed for you, because it is a dry chamber, everything is dry, perfect condition, no problem, but situations will come where you have to understand transition flow and choked flow. So, for a gas flow, I want to conclude now. In vacuum systems, we will slowly enter from various flow directions, from choked flow or turbulent flow, then laminar flow, transition flow, finally molecular flow. Okay. Different things happen at different situations. Since this lecture is for transition flow and Knudsen flow, transition flow occurs at the end of the onset of roughing and at the beginning of high vacuum pumps. Sometimes the choked flow occurs when you are venting it to the atmosphere, when gas inlet is there, or in the initial instant of evacuation, etc. Okay. So, conductance in the transition flow is computed by taking a combination of laminar flow conductance and the molecular flow conductances. Mostly it happens in the Knudsen number of 0.5 to 0.01, which is typically occurring at the end of rough vacuum and beginning of high vacuum. In choked flow, throughput is independent of downstream, that is the main point. This is normally applicable in venting of the chambers, which you have to vent if you want to take your product. You have to do slowly, and you have to apply some gas inside, that is also in a way choked way. You cannot introduce suddenly gas, then you will get into accidents. Okay. And controlled gas inlet or intentional reduction of initial pumping speed to avoid debris, all these choking flow problems you have to understand properly. Okay. An engineer should calculate the conductances and pump down times in all the situations, starting from the atmosphere up to his level. If end of the vacuum is only rough vacuum, he has to only take care of the little bit of turbulence and laminar and only transition. Otherwise, he has to take care of this, and if he is only 100 or 200, even transition flow is not required, only laminar flow. So, like that different equations are there at different conditions. You have to take the sigma of all those things if you want to get the integrated time, and if it is within the reasonable time, so that your process can start, you will be happy, vacuum will come, your boss will be happy, product quality will be good. So, with these ideas we will stop at this point of this transition flow and choked flow. In the next class, which is the end of this fluid flow, we will take some few hints of various things, we will show some examples. Anyway, these things will be dealt again in applications, but we will try to give you some examples with numericals, because without numericals just talking mass physics may bore you. So, that is the last lecture of fluid flow. We will do something about calculations using typical systems that we encounter in our applications. Thank you very much.